my name is Alex Nimmo. I'm part of Section A6 for Aerospace 305, and today I'm going to be talking to you about our Lab S3 Shear Center experiment results and discussion. We did a Shear Center experiment on L and U beams in collaboration with Jason Miller, Robert Batchelor. Our instructors were Dr. Beck and Dr. Dare, and our teaching assistant was Ben Sterator. The date of the experiment was November 13th, 2019. We're going to go over the introduction of the experiment, the experimental procedure. We're also going to go over the results and discussions and a conclusion of what we actually found. So the introduction. So in this lab, we took two beams, an L-shaped beam and a U-shaped beam, and we went and tested them in room 47 in Hammond. We found the shear center of the two beams using, in figure 1, the shear center apparatus. This little thing, we just loaded the beam up there and we did our little experiment, which will be described later on in the next slides. We expected the shear center of the L beam to be at the corner of the beam, and we expected the shear center of the U beam to be left of the beam. And the way we found that was doing the theoretical shear calculations. So for the L beam, we found that the shear center should be at the corner of the beam, denoted by this little blue dot right there. And also for the U beam, we found that the shear center should be about 0.432 inches left of the U beam, which is what we predicted, and hopefully what we find later on in the experiment. And we also found that the Y position should be 0. It should be, since it's a symmetrical beam, it should not be off the axis. And the way we found those was using these shear flow equations. So we took this big shear flow equation, the QS, and we canceled out a bunch of terms. Since the beams are symmetrical, the IXY is canceled out, and it goes into these little two terms right here. And then for each beam, we did the analysis of it, and we found that the second moment of inertia was this equation, right, found by this equation. And then we also found that the A to X position was found by this, and that's where we got the 4.32 inches that we used as our theoretical shear calculation. And we also found that the Y A to position was Y over 2, which makes sense because Y over 2 is...
Hi, my name is Robert Batchelor. I'll be covering the calibration procedure, the calibration results, as well as the experimental setup and the experimental procedure. For the calibration, what we did is we mounted a beam in the apparatus as if we were going to run the experiment. We then loaded the beam back and kept it in that place. We then pulled the linear potentiometers back and loaded 2 blocks of known width between the linear potentiometer and the load bar. We then took data with the linear potentiometer for both blocks in between, for 1 block in between, and for no blocks in between. We did this for both linear potentiometers, and from this, we were able to calibrate them using the displacement from the blocks to get a graph. This is the results of our calibration. As you can see, the lines for both linear potentiometers lie on top of each other enough that the calibration factor for one will be used for both. From this graph, we got a calibration factor of 0.643. For the experimental setup, we mounted a beam in the apparatus and mounted the load bar on top of the beam. We then loaded the beam with the weight going on the 0 notch of the load bar. On your right, you can see the apparatus with the load bar, the load wheel, the weights, and the loaded beam. With the experiment set up, we took a data point with the loaded beam at the 0 point on the load bar. We then moved the load 1 notch to the left, and we recorded another data point. We did this 5 more times on the left, taking data points each time, and then 6 times on the right, taking data points each time.
Hi, my name is Jason Miller, and I'm going to be talking about the experimental results of the Shear Center lab. Right here is the L beam results. Now, the shear center is located on the intersection of these 2 linear lines, one being the left linear potentiometer and one being the right linear potentiometer. Now, the intersection of these lines is where no twisting occurs, which is thus the location of the shear center. Looking at these 2 lines, they can be seen as fairly accurate, as they have high R² values, roughly in the area of 0.99. Now, looking at the results of our L beam, we can see that the shear center is roughly at 0.2. This does not match our theoretical results, as the shear center for an L beam should be at the corner, 0. This is because the shear flow runs from both the sides towards the corner. Now, this is most likely due to operating errors. Now, looking at the U-beam, we can say that the intersection is roughly around negative 0.2. This data can still be seen as accurate, as one of the linear potentiometers has an R-squared of 0.99, but the other is less accurate at 0.95. Now, this data doesn't match our theoretical results either, as this should be roughly at negative 0.4. Looking back at our L-beam, if this were to be shifted to the 0 point, approximately 0.2 inches, and the U-beam would also be shifted left 0.2 inches, which would more closely match our theoretical results of negative 0.4. In conclusion, our shear center procedure was not as effective as it should have been, but this is most likely due to operational error. This is likely due to that the initial aligning of the L-beam was not straight down the center. Now, some other errors that could have caused this is previous loading of beams, which would impact our results, as we assumed an ideal beam. The two conclusions we came to, though, is that the shear center for the U-beam is in the negative section, roughly around 0.4, while the shear center for the L-beam is at the corner of the beam. In the future, we would either use better beams or align our loading more around the 0 point of the beam so we could get better data. Thank you.